Hello, this is Mrs. Scarple, and I'm going to take you through the first part of Unit 1, Lesson 1, Quadratic Functions. In this lesson, the focus is on being able to model a growing pattern with tables, graphs, and equations, and to analyze the type of growth exhibited by the pattern. And what do the different representations tell us about a pattern? So our first pattern is similar to the bars you see for cell phone signal strength, except it's broken down into a series of squares. So what we're going to do first is, assuming the pattern continues, is draw the next figure. So for figure 5, if I look at these, it looks like I'm adding a row each time, and the row that I add has one more than the row above it. So for figure 5, we're going to have five on the bottom, and then we have 4, and then we're going to have 3, 2, and then finally 1 on top. So this is figure 5. As we move along, for number 2 is how many blocks will be in figure 10? Well, to do that, we might want to create a table. And I'm just going to put the table on this screen with the figures. So my table is going to have the figure number as the top row. And we're going to have the number of blocks for the bottom row. And we need to go out to figure 10. So figure 1 has 1 block. Figure 2 has 3. Figure 3 has 1, 2, 3, 4, 5, 6. Figure 4 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Figure 5 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 blocks. So we have 1, 3, 6, 10, 15. Now if we look at this pattern, from figure 1 to figure 2, we have 2 more blocks. From 2 to 3, we have 3 more blocks. From 3 to 4, we have 4. From 4 to 5, we have 5. So you might say that the number of blocks added increases by 1 each time. So we'll add 6, and then we'll add 7, and then we'll add 8, 9, and 10. So 6 plus 15 is 21. 7 plus 21 is 28. 8 plus 28 is 36. 9 plus 36 is 45. 45 plus 10 is 55. So figure 10 is going to have 10 blocks. Now, we also need to examine this sequence and find a rule or formula for the number of tiles in any figure number. So first thing I'm going to do is create a graph of our pairs. The bottom axis, the horizontal axis, will be the figure number, and the y-axis, the vertical axis, is going to be the number of blocks. And I'm just going to do this for the first 10 figures. Because those are the values we know. And since figure 10 has, oh, I see that I wrote the wrong number. Since figure 10 has 55 blocks, correct this, we need to have a scale that will allow us to go up to at least 55. So I'm going to go by fives and label every 10. 20, 30, 40, 50, 60. And plot our points. So figure 1 had 1, figure 2 had 3, 3 had 6, 4 had 10, 5 had 15, 6 had 21, 7 was at 28, 8 was at 36, 9 is at 45, and 10 is at 55. Now if we look at the pattern these points are making on the graph, hopefully you can see that it's not forming a line. If it were a line, it would be straight, but this is curved. Because it's curved, we're not going to be able to write any linear equations. So I'm going to start with what we call a recursive formula. And a recursive formula starts with notation of what the first term is. So f of 1 was 1 block. Now the 1 in the parentheses is the figure number, and the 1 that it equals is the number of blocks. For the pattern to continue, we're going to say f of n, that's meaning the number of blocks for any figure number, is going to equal the previous figure number my mind drew a blank there a minute. So the previous figure is what this notation stands for, plus, let's take another look at that table. To get the second figure, I added 2. To get the third, I added 3. To get the fourth, I added 4. To get the fifth, I added 5. So what I end up adding is the figure number. So we're going to do plus n, because that n is our figure number. So that's the recursive formula. But if I wanted to go out to how many blocks are in the 50th figure, I wouldn't want to do this table, I wouldn't want to do this recursive pattern. In that case, what we're going to look for is the explicit formula. So I'm going to go back to my figures, and I see that these figures, other than the very first figure, look similar to triangles. And one thing I know is that triangles and rectangles have a relationship if I look at the area. So I could say this has an area of 1, this has an area of 3 square units, 6 square units, 10 square units, 15 square units. I also know that if I take my shape and I add on the same number of squares and create a rectangle, I can find a relationship between the area of my original figure and my rectangle. Now, area of a rectangle. Equals length times width. So if I look at my dimensions, I have 2 by 1, I have 3 by 2, I have 4 by 3, I have 5 by 4. As I'm looking at these dimensions, I notice that one dimension matches the figure number. The other dimension is one more than the figure number. Now I said that there is a relationship, and I'm just looking for the area of the original. Well, how much of the rectangle is my original figure? Hopefully you're thinking to yourself, well, it's half as many. So to find the area of our figure, we want half as many, just like in a triangle, it's 1/2 base times height. So our explicit formula that we're going to have is going to be f of n, meaning we can find this for any figure number, is going to equal 1/2 of n times n plus 1. So the n is the figure number, the n plus 1 is the next number. Or next term, whatever you want to call it. Now I can also distribute this and have an equation that looks like 1/2 n squared, because n times n is n to the power of 2, plus 1/2 n. This power of 2 tells me that what we have is a quadratic pattern. So a curve that looks like this has a quadratic pattern. Our recursive formula, our explicit formula, has a quadratic pattern. If we go back to the table and I look at the next set of differences, so we call this first row the first difference. If I look at this for another row, from 2 to 3, I'm adding 1. 3 to 4, I'm adding 1. 4 to 5. I keep adding 1 each time. We call this the second difference. So because the second difference is constant, we can say that the first difference is linear, because that first difference is going up by the same amount every time. So when your second difference is constant, you're going to have a quadratic pattern as well. So that is our example with quadratic patterns. Let's take a look at what happens when we're comparing the perimeter. So we're going to use the same sequence of figures, but we're going to look at perimeter. So the first figure was 1 square. And perimeter, if you remember, is the distance around. So in figure 1, our perimeter is 4. Each side is 1 unit. For figure 2, our perimeter is 1, 2, 3, 4, 5, 6, 7, 8. For the third figure, our perimeter is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And for the fourth figure, one more row. We have a perimeter of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let's take those numbers and create a table. So my top row is going to be the figure number. My bottom row is going to be perimeter. So figure 1 has a perimeter of 4, figure 2 has 8, figure 3 has 12, figure 4 has 16. If we look at these, they're going up by 4 every time. So our recursive equation is going to be f of 1 equals 4, that first value. For any figure after that, it's the previous term plus 4, because we're always adding 4. The explicit equation, if we look at these numbers as well, the relationship between 1 and 4 is 1 times 4 is 4. With 2 and 8, 2 times 4 is 8. 3 times 4 is 12. 4 times 4 is 16. So for the explicit equation, we're going to say that f of n equals 4 times the term number, so 4n. Now, this had that constant difference right away. So the first difference is constant. So if we look at what a graph of this would look like, and I'm going to place the figure number on the bottom. And the perimeter on the side. One, two, three, 4. And because we're always adding 4, my scale can be 4. 4, 8, 12, 16. So our first figure was 4, our second figure was 8, our third figure was 12, our fourth figure was 16, and if we look at this, it's going up by 4 every time. We're also getting a linear pattern. We have a linear equation for our explicit equation. F of n equals 4n. Our slope is 4, and we don't have a y-intercept. If we did, it would be 0, and we could write plus 0. So we have first difference is constant for a linear pattern. And we talked about the second difference is constant for a quadratic pattern. So some things to take away from this lesson. For quadratic functions, in the table, your second difference is going to be constant, so a constant second difference. For a quadratic, you're also going to have a curve that has a minimum value. You can write recursive equations. Remember, you have the first term. Not all of them look like this recursive equation, so I'm just going to make a note that this is an example. But you will be adding something n. Maybe it's a linear first difference, but it increases by 4 every time, so we might have 4n here. But this is a linear term, this n. The next term is found by taking the previous and adding a rate of change. In this case, it's a linear rate of change. And then an explicit equation is often a model for area. Quadratics are often used to compare areas or talk about areas. And again, this explicit equation, which is the same one that we had for our figures, is an example. It's not going to be the same quadratic equation for every quadratic pattern, but it will have an n squared term and it will have an n term. So the n squared is called a quadratic term and the n is called the linear term. And this is where we ended the first part of lesson 1 for unit 1.